welcome to today's webinar where we carry on looking at structure-borne sound sources. And the idea today is we're going to expand upon the fundamentals that were introduced in that first webinar, and then we'll also recap and reinforce those ideas. So don't worry if you've forgotten something from the first webinar. And we're going to start today with a presentation by Martin McNulty on structure-borne sound sources. And the emphasis there is going to be on the kind of sources you find in buildings, and we're going to look at calculations and measurements of the source mobility. Martin will then run through some demonstrations that were filmed in our lab, and those will illustrate the effect of different types of mountings for the machinery. That will be followed by a presentation by Andy Elliott, who will focus on characterizing the active properties of an operating source, and that will investigate an engineering method and a precision method, which will cover a full range of engineering applications from building acoustics through to the automotive and aeronautic industries. So just like before, the microphones will be muted during the lectures and demonstrations, but if you have any questions, just please put them in the chat and we'll pick them up in the period after the presentation or after the demonstrations. Okay, so now I'll hand over to Martin.
Okay, hello and welcome to webinar 2 of the UKAN SIG-VA Vibro-Acoustics Masterclass. My name is Martin McNulty, a consultant, and I lead the vibration group at Hawley, and today I'm going to be presenting the first of 2 sessions on the topic of structure-borne sources. As with Josh's one in the first webinar, this slideshow is pre-recorded, though I'll be back online at the end of the presentation to take any questions. Okay, so a quick overview of what we'll encounter in this presentation. First, we'll run through some common examples of structure-borne sources in buildings, and we'll discuss why there may be a temptation to over-idealize these, perhaps as single-degree lumped parameter systems, and we'll explore why that can sometimes result in missing the complexity that is ultimately needed for a successful prediction. And from here, we'll remind ourselves why we can't simply measure at the foot of a machine and how, compared to an acoustic source, we need more than one descriptor when we're trying to predict power transmission. And at this point, we switch to the main focus of this presentation, which is source mobility. And we'll begin by thinking about what efforts we might have to go to get high accuracy values and why these might not be so practical in everyday use for the practitioner. And we'll then go on to see how we can instead use convenient and, well, surprisingly simple expressions which nicely approximate simulation and also real-world experimental data. So, as promised, we'll start by thinking about typical sources in buildings, and keep in mind that anything that can whir, click, spin, thud, etc. has a potential to be a potential structure-borne sound source, and more importantly, a cause of annoyance. And if it wasn't annoying, then we might not need to assess it at all. So in the home, we've got everyday items such as fridges, washing machines, boilers, whirlpool baths if you're lucky enough to have one. And these alone might not sound like high vibration generating pieces of equipment, but we have to remember that sometimes they can be in areas where the background levels are quite low. And in reality, I probably spend a good chunk of time working on structure-borne sources in mixed-use facilities and also science and research environments. In science and research environments, you have to ensure that aspects such as building services, pumps, chillers, air handling units, that type of thing, don't generate vibration which would interfere with the usually ultra-low noise and vibration requirements of scientific equipment such as electron microscopes. In mixed-use developments, and this is becoming a bigger problem fueled by ever-increasing urban densification, we see more and more the introduction of gyms into sensitive areas. Quite often we'll find gyms within office buildings, within residential developments, within shopping centres, and the combination of shared uses can lead to high source activity and low receiver tolerance. And this poses a unique problem where the dropping of weights or people running on treadmills can generate large amounts of vibration, and ultimately this leads to complaints and in some cases legal disputes. And staying with the fitness example, this animation shows a few of the problems that the structure-borne source, our robot on a treadmill in this case, can cause. Vibration at the feet might produce some near-field effects. There might be some near-field sound radiation, but also the vibration generated can move away from the structure and propagate freely through the building. At each structural interface, structural junction, the attenuation is usually much lower than that offered by the airborne component of floors, walls, etc. And as such, structure-borne noise can propagate freely through a building and affect not just its immediate neighbour, but neighbours beyond that as well. And when assessing this type of source, if we were to stick with the treadmill example, you might be tempted to idealise it as a single degree of freedom, i.e. a mass on a spring. And it certainly has all the elements that you might expect in such a system. We could reduce the treadmill and the user to a combined mass. We could think about the contact points as the spring between that and the structure beneath. And the disturbing frequency, the operating frequency, could be that of the pace frequency set by the runner. And the reality is that the system's more complex than this, and if we were to measure at the contact point with the structure, we wouldn't see the sweeping sine wave that we would from a simple harmonic system. Instead, we'd actually see a series of impacts, and the impacts would be spaced apart in time by the running pace of the user. And when we analyse an impact in the frequency domain, we don't just see a single tone, we'd actually see a broad spectrum of vibration. And this is what makes the problem more complex. And in terms of structure-borne noise, we've got a much broader palette of frequencies to treat rather than just at one discrete frequency. And let's return to some considerations which we explored in Josh's presentation and ask the question why we just couldn't measure next to a piece of machinery and use that in our assessments or predictions. And as you might recall, the answer is that the receiver affects the power transmission. And we demonstrate that here with a small simulation comprising two slabs, a thin timber one and a thicker concrete one, both of which are suspended by 10 Hz isolators, which you can see as springs in the pictures on the right. The plot bottom left shows that aside from the rigid body behaviour at 10 Hz, the similarities end there. The concrete system in general has a lower response and fewer modal peaks, where the timber system has many modes and a generally higher level of vibration. Both these curves are for the same force input, therefore we must understand that if these measurements were carried out independently by two different people who assumed that the results would be sufficient to characterise the source, they would come to different conclusions about the level of vibration that source would produce. As such, the method is insufficient and we must instead look for a better means of source characterisation. Okay, so this leads us on to the topic of source mobility. But before we do, we remember that we need a number of descriptors to describe structure-borne power, and this differs from the acoustic problem where we could simply use sound pressure level measurements over an enclosing envelope of a source. That's one way to derive the sound power, and provided we were in air was our medium, then that sound power would not change. It's different in the structure-borne case, and as we said, without going back into too much of the detail of Josh's presentation, it's worth taking a moment to refresh our knowledge and remind ourselves of these quantities that we need to predict power transmission. And that's the mobility of the source, the mobility of the receiver, and either the block force or free velocity of the source. Andy will be talking about block force and free velocities in detail within his presentation shortly after mine. But this leaves us with the passive property of the source, namely the source mobility, or its inverse, the source impedance. And this is a measure of the structural dynamics of the source itself. It's a passive quantity, and it's the focus of the remainder of this presentation. And since sources come in all different shapes and sizes, we'll spend a little bit of time now thinking about the level of effort we might need to go to in order to determine this quantity directly. And we've seen from some demos that a way to get source mobility directly would be measurements. But we have to remember that the source mobility is an independent quantity, and therefore its dynamics must not be affected by any other structure. Since we can't have sources floating in air, we'd likely have to do something along the lines of suspending it from springs and measure its force to velocity, velocity, displacement, acceleration responses at would-be contact points with the receiver structure. This would necessitate the purchasing of force hammers or shakers, multi-channel systems, and a suitable test rig to perform the test. And we'd also have to ensure that the mass spring resonance did not affect or colour our measurements when we look at the overall frequency response. From a practitioner's point of view, such an environment or perfect laboratory conditions are rarely afforded to us. So if we can't measure something directly, or it's problematic or not practical to do so, we could always undertake some simulations. And there are some obvious advantages in doing this. We don't need a laboratory for one, and we can also try out multiple configurations like you would perhaps in a product development setting. And this is good if we want to optimize sources or get an understanding without having to physically get our hands on one. There are, however, disadvantages. Firstly, we need the software, which doesn't come cheap, and the simulation procedure, much like the measurement, requires certain protocols to ensure that we don't end up in a rubbish in, rubbish out type situation. Further to this, the computational effort to capture a broad range of frequencies or mesh densities to resolve large complex geometries can also be significant, and runtimes aren't quick. They can take hours, days, or in weeks in extreme cases. And we were told before on webinar 1 when Carl made a reference to production lines, and even with the best production line, there will always be some slight variations in material properties and boundary conditions. And if we run a simulation, particularly a complex simulation that takes hours or days to run, that is a snapshot in time for a single set of material parameters. So for us to capture the real world variation, we may have to run a simulation a number of times to gain a statistical impression of what the actual response might be, or the variation in the response. And the example we've got here is that of a single glazed panel, and we've randomized the inputs of density, Poisson ratio, Young's modulus, and damping in a randomized way, and ran the simulation 100 times, and we've got this response which we've tried to run through a mean line, which is shown in red, and then the mean plus 2 standard deviation response, which is shown in the dashed curve. So as we build the complexity of a source, we might also have to run it in a sort of Monte Carlo stat type fashion, and again this could add to the delay in getting results that we need, especially if we're working to tight timescales. And that brings us to a point where we think, okay, we can't measure it practically, we can't do a simulation, we probably haven't got the time, so what do we do? And as we've seen in previous presentations, we do have a series of simple expressions that we can use and that will get us in and around the answer pretty quickly, but the expressions that we'll use, we'll see, depends on the type of mounting connection to the intended receiver structure. So the mobility of a contact point is dictated not just by its material properties, but also the geometry of the mounting arrangement. And if you think about it, you can usually rationalize supports into a number of discrete groups, and not that many. In the following slides, we'll see that the mobility of compact sources, flanged or cantilever type bases, plate bases, and those of frame beams can all be described surprisingly well with simple expressions with relative ease. And in many of the cases we'll see, the root of how we get to these expressions lies with the behaviours of simple idealised mass stiffness or damping elements, which we consider in isolation to derive mobility terms for each. These, along with expressions for the behaviours of infinite plates and beams, provide us with all the tools we need to use in the real world. So now we'll spend a little bit of time looking at some of these expressions in more detail and see how well they represent the real world condition. Starting with mass mobility, we've seen this already, but the expression here is simply 1 over j omega n. It assumes that the mass behaves as a single point mass and experiences no rotation effects, though this can be accounted for via some additional terms to those shown. We've seen that the mobility is frequency dependent and it decreases with increasing frequency. So let's see how this stacks up in the simulation environment. Here we've got a kettlebell, and the chart on the right, the red curve, shows the mobility we get when we perform a finite element simulation and apply a vertical unit force at the base. The response is compared to the green curve, which we computed in a spreadsheet. You can see there's excellent agreement between the two, and the only real benefit of the FE model will be to tease out the higher frequency response, where the influence of the handle begins to affect the mobility, as shown in the animation on the left. These frequencies and above might not be necessary if we were assessing impact from such sources, as it's generally the low frequency thud which is the region of concern. And now let's compare a similar calculation to actual measurement. In this example, we'll go back to our pump which we saw in demos for seminar 1. We recall that the mask-like component describes the low frequency aspect very well, though as you may recall, this was up to a point where we encounter anti-resonance before the mobility increases as a result of the cantilever arms, which are best described as lumped stiffness elements. And you'll be pleased to know that the stiffness element for a cantilever support can also be represented in a simple form. The equation you see before you is derived from lumped stiffness mobility definitions with substitutions for cantilever stiffness. As with mass elements, the trend shows frequency dependency, though this time the mobility is directly proportional to the frequency, driven by the omega term being on the numerator. And with that in mind, let's quickly return to our results for our famous small pump. We now see that the mobility region above the anti-resonance dip is described incredibly well by a spring stiffness-like mobility of a cantilever. This makes sense since a freely supported element, as it was in the demos, would allow cantilever action to occur once able to do so. Given the cantilever in this case is fixed to a source of interest, we now understand why we have two regions in the mobility response, and both are described well by the mass and stiffness equations. Whilst we don't predict the depth of the trough at the anti-resonance location, we know that we can expect one to occur as it roughly coincides with the intersection point between our two predicted curves. And to bring this home, let's have a look at a simulation of a similar arrangement. Here we can see the simulated driving point mobility curve at one of the mount connections, and again our two simple expressions provide an excellent representation of the overall response. The animations show the three regions of interest. Firstly, the rigid mass region, the top animation, where the whole unit moves with one, i.e. we have rigid body motion. Second, we see the anti-resonance switchover point, where the support is stationary but the rest of the pump is moving. And finally, the stiffness control region, where the motion of the fan is minimal and the cantilever edge begins to flex. So we've covered mass and cantilevers, but for sources comprising plate bases or those formed with plate-like elements, we need to use the characteristic mobility for infinite plates. We've seen the equations in a number of presentations now, but it's worth reinforcing the fact that the expression has no complex or imaginary part, nor does it have any frequency-dependent item. A plot of the infinite mobility therefore takes a single horizontal line, making it analogous to that of a damping element. And as in previous presentations, we've seen that the response of an infinite plate tends to the average response of a finite plate of the same thickness. The equivalent agreement between finite and infinite structures improves at high frequency, and also in the cases where we have high damping, as in both the peaks are less pronounced, and we've also seen that we can envelope these with maximum and minimum expressions. And again, returning to measurement scenarios, we've seen plenty of times now that the characteristic expression fits the average response really well. This is reinforced in this plot, which illustrates the measured mobility of a plate base at 4 points. The average response, which is the thick black line, is well approximated by the infinite plate expression, which is shown as a dotted line through the middle. Moving on, we'll now look at flanged cantilever structures, which seemingly increases complexity compared to our previous examples. What we will see, however, is that flange cantilever sources can be approximated as a transition between rigid, stiffness and infinite plate mobilities. So let's develop this and compare another simulation to our simple analytical models. In this one, I've included some animations to show behaviour at key points to aid our understanding. In the plot, we have the black curve, which is our FE model output. We also have the green curve, which is our mass mobility, our cantilever mobility, which is shown in blue, and the infinite plate mobility shown in red. In the mass region, the animation shows that the pump and its supports move as one, and rigid body motion is observed. When our compact source, mass mobility and stiffness cantilever mobility intersect, we have the anti-resonance switchover point where the edge of the cantilever exhibits significant reduced vibration. Once we pass through this anti-resonance, we see in the bottom left animation that the cantilever motion describes a response with very little motion in the body of the pump. Finally, we see a series of sharp peaks around 1 kHz and above. These are the results of modes in the plate element of the flange. In the corresponding animation, we see most of the activity is constrained to this plate, and the pump itself remains, in vibration terms, fairly quiet. And again, as we do, we step outside of the simulation environment and look at measurements on a real-world flange base. And we can see again that the three transitional areas of rigid mass, stiffness controlled from the cantilever supports, and infinite plate mobilities, again, draw a nice average line through the measured response. So again, our simple expressions provide a nice real-world approximation. When we start to think about framed connections to sources, things become a little bit more complicated due to the numerous arrangements that can exist. However, all is not lost, and as we've seen with timber-like structures, we can simply revert to infinite beam equations to give us a good indicator of general behaviour. And in this example, we've done exactly that. Our simulation has been plotted against the characteristic beam equation, and as we've seen for all infinite situations, we don't capture the peaks, but we capture the average trend. And returning once again to a measurement condition, we can see that our average mobility, taken from an average of 8 measurement locations on a frame base, follows the curve of the infinite beam, which is our dashed line, pretty well. So, to summarise what we've seen in this presentation, it's probably best to think of it as a series of pros and cons. Thankfully, the pros outweigh the cons, but hopefully you'll see that using simple expressions for source mobility gives us a quick way of predicting the average response. It removes the need for costly simulation and measurement setups if we are working in an engineering level of prediction. And it's simple to execute. We don't need any coding experience or fancy software. All of the equations that you've seen can be executed in a spreadsheet package. And perhaps one of the most powerful aspects of this method is it can be used to sense check any data that we receive or any data that we were to go out to site and measure or actually come around to simulate. If our characteristic expressions or our mass or stiffness or damping elements don't approximate well what we've seen, then we know that something's gone wrong. And all of this convenience does come with some downsides. So what we've seen are trend-like types of response. Even when we envelope those, we see some pretty big deviations from the average line. Values of 10 dB at low frequency can be expected. And it also misses these maxima and minima. If this was of critical importance, or if we were trying to do predictions in sensitive environments with sensitive machinery, we might have to look in that in a little bit more detail to understand where these frequency spikes might occur. And as we've seen for frame type bases, the more complex the connection type becomes, we do lose some accuracy, though we can still get the trends overall. Okay, so in summary, we've seen that measurement of vibration at source doesn't adequately provide data which we could reliably transfer between different constructions, different assessment scenarios. And briefly, we know that compared to an airborne source, a structure-borne source requires active and passive descriptors to be faithfully characterised. And in this presentation, we focus mainly on the passive element, which is the mobility. And we've seen that for many types of machine mounts, the mobility of the source can be simplified to easy to use expressions which tie up well with observations and simulations, and as such should be of use to the practitioner moving forward. And that concludes my presentation. Thanks very much for your attention. I'll be on hand now to answer any questions that you have. And thanks again for listening. Bye-bye.
First of all, we'll talk about the mobility of the cantilever and a pump which we've seen before, and we'll see very nice hammer action there from Gary. And this one we've seen before. So we start off with a rigid mass with a cantilever arm attached to it. I thought we'd start again with this one because it's a nice comparison to see how an idealized source mobility actually matches up well with a real world example, which is kind of the point, really, making sure that we can convince ourselves that these expressions hold up in the real world. So we've got there the mass and spring-like behavior being approximated very well. And here we go again. And we're getting the multiple hits at the contact points. This time we've got our small pump. And there we go. As per the slides on the left and also the presentation, we can see that the behaviours are matched quite well. I'll pause it here briefly. We encountered this yesterday, but the results at each of the contact points are slightly different and they come in pairs, and that's just because the centre of mass is the distance from the centre of mass to the contact points is different in each scenario, so we'll get slightly different responses in the mass region. Okay, so moving on to a plate type base. Same principle applies, so accelerometer located in the fixing point for where our receiving structure would be, freely suspended on some bungees. And if we don't have the results in this video, but when we analyze this, it goes straight into, this is the narrow band response on the top and then the third octave on the bottom. And you can see if we were to draw the straight line through the middle, that would be our infinite beam response, infinite plate response, sorry. And again, it's quite clear in the third octaves that we get really good agreement, you know, particularly at high frequencies where the peak starts to become pronounced, and it ties up very nicely. I mean, we do get a little bit of deviation at low frequencies, but that's just very much the nature of the beast. Okay, so here we've got a slightly thicker plate, but we have some flange connections here. So again, this would be the contact point between the source, count this as the source, and the receiving structure. And we don't see the results. We see the results on the left-hand side here in the accompanying slide. And we've got the two, we can see the two transitional regions. We've certainly got this mass-like behavior that's that decreases with increasing frequency. We've got a bit of a transition, and then we go into our plate-like response. So again, you know, our two simple expressions that we would use in our that we saw in my presentation would fit this quite well. And this demo is actually reinforcing the point, really. I mean, to look at this particular bit of machinery, we'd think it was a lot more complicated, but actually, when we look at the response, we can still use our simple expressions to describe the mobility curve really nicely. So we'd still get mass effects, we'd still get spring-like effects before transitioning to the infinite plate response. So provided we have an idea as to what type of mounting arrangement we would have, you know, we've always got an opportunity to estimate the source mobility from these expressions. And then as we sort of came to at the back end of the presentation for frame bases, this could take any type of arrangement really. And obviously you can see the accompanying mobility curves here. They vary quite a bit, but when we take an average, you know, again, we get excellent agreement with our infinite beam expressions. So even though things can start to look complicated, it's still really nothing to be afraid of, because we can certainly get the behaviors and get the trends with, you know, fairly little effort. I think we'll stop there. Okay.
Thank you. Right, are there any more questions on those videos before we move on? Okay, Martin, do you want to take that one?
Okay, when doing these types of tests, would using different thicknesses, strength, bungee cord affect the reason? If so, how do you know which to use? Okay, well, I mean, there's going to be a mass on a spring resonance. There's no getting away from that. So that will limit your frequencies, but should be a fairly you should know what that frequency is. You could just you could do the rough-handed way, and you could literally physically displace the thing that you were looking at, and you'd be able to see that, and you'd see that on the readings quite clearly, so you'd be able to discount that. So I think you would just have to take some efforts before your experiment to understand where that mass spring frequency exists, because around that you'll get amplification, you won't get a true response. So yeah, you have to sort of go back to some basic vibration theory and make sure that you've tuned your arrangement in the right way. But it's a good point that it does exist, and because we can't suspend these things in free air, that there'll always be this factor to account for. So yeah, hopefully that answers the question.
Okay, another question from Paul Melvin. Looked like the test was taken on a table. Yeah, I mean, yes, to elevate things up for the video recording, that was done. But once it's resiliently suspended with those bungee cords that we've just been talking about, you shouldn't see any effect. Quite often what people do when they have something complex for the first time is they'll set it up, take a series of measurements, tweak things, change things, and see if there is any change, more than a dB. And if there is, then they'll start to be concerned about how it's suspended. So there is sort of, it's an experiential thing. So people who've done it a lot, will have a rough idea how to do it. Andy might comment a bit more on different machinery here.
Well, one thing you can do for experimenting with bungee cords and things like that, for it to be free, you want the natural frequency of the mass sprung resonant on the bungee cords to be as low as possible. So ideally you use very lightweight bungee cords, but obviously as you put more weight on those, they get more and more tension. So it's just playing about really and exciting the structure to try and just get it to have a really low frequency bounce. And you want that frequency at which its rigid body motion on the bungee cords, you want that to be lower than the first frequency of operation of the machine, basically. But yeah, it's very much a experience thing.
Okay, and the next question is a good one. So what if you're dealing with a machine which is too large to bungee up? And that's a really good link into Andy's talk now. So thank you, Martin. So so Martin was looking at the passive properties of the source, and now we're moving to Andy, who will look at the active properties of the source, and in there will be the answer to your question. So Andy, hand over to you now.
Can everybody see that okay?
Yes.
Very good. Okay, so this is webinar 2, as you'll all know as you're here. I'm Andy Elliott. I'm a reader in vibroacoustics at the Acoustics Research Centre at the University of Salford. I'm going to talk about what we're referring to as advanced methods for other engineering applications. Meaning mainly sort of beyond building acoustics, but also including building acoustics. So you just heard from Martin. He's been talking about structure-borne sound sources in buildings, the basic source types, and simple calculations of mobility and how to obtain characteristic values of mobility from just simple elements such as beams, plates, and mass and stiffness elements. And he's shown how you can make some calculations of simple source mobility behavior and how well they compare with measurements. He's shown some demos and results of those measurements, and we've had a couple of questions. So the last question leading particularly well into this presentation, as Carl's mentioned. So in terms of advanced methods for other engineering applications, what I'm going to talk about first of all is the measurement of source activity. There's a couple of ways of getting intrinsic properties of a source. One is to make it completely free, as we've just discussed, but then there's the other extreme of the case where it's the opposite of free. Instead of measuring the velocity, we want the force which is applied to an infinitely stiff and immovable object. And there's a couple of ways for obtaining that source activity. One is the reception plate method, which is used to obtain single equivalent block forces and free velocities, as well as mobilities actually. And then there's another method so the reception plate method's been very widely developed at Liverpool University, but it's something we also use ourselves for certain applications. And then there's another method that we've been looking at Salford, which is an in situ method, which is generally for more precise estimations of prediction of structure-borne noise using this in situ block force approach. So as mentioned before, we need two data sets to predict structure-borne sound. The first being the source active properties. In terms of intrinsic properties, that could either be the free velocity or block force. If we use the installed velocity or the installed force for one machine on a specific structure, you'll find that that same machine, when installed on a different structure, will have a completely different installed velocity and a completely different force. So the installed properties on a specific receiver are not intrinsic. We have to put these extreme boundary conditions on, either entirely free or entirely blocked. And then there's equations that we can use to use those extreme cases to predict via the source and receiver mobility. We can predict the transfer of power, or if we're using vibroacoustic frequency response function, we can actually predict structure-borne noise or vibration. So Martin has already been through in quite some detail how to obtain these source passive properties, which can be obtained by measurement or modeling or using simple connected elements. A more challenging problem that you tend to face when you're faced with dealing with a structure-borne sound problem is how to obtain the source active properties. And the source active properties are those properties that we measure while the machine is under operation. So either the free velocity or block force. I'm just going to have a quick look at those now and look at some of the pros and cons of both of them before explaining the two methods that have been developed to make those measurements a little bit easier. So in terms of the free velocity, we want the vibration of the contacts of the machine to be completely free and unaffected by the mount. The common way to do that is to, as you've just seen, hang the source by bungee cords, or you could put it on air springs or some other resilient rubber, and you want the natural frequency of the mass of the machine on the stiffness of the bungee cords or support to be as low as possible, because above that resonant free mass spring resonance of the system, that's when your system is actually truly free and you get a proper measure of the free velocity. So basically you want something really, really soft to support it, but then that doesn't lend itself to all sorts of machinery. For example, a motor like this, you'd probably get away with it. But if you wanted to run that motor in a representative way, you probably want to apply some load to that electric motor. So it'll probably be going into a gearbox, which then transfers the power to something else. And when it's running under load, the forces inside the motor are different to how they would be if it was running freely. And I think you can see in that instance, if we connect something to that shaft and try to run the motor, it's just going to spin around rather than doing the job that it's supposed to do. So that is a big drawback of the free velocity method, and why we've been looking at other ways. For certain examples like the pump we saw, where all the mechanisms are self-contained and it's sort of self-loading, you can hang it up on bungees and get the free velocity. But there are many cases where it's not actually feasible at all to measure the free velocity. Same is the case for some very big and heavyweight machinery. Another example where the free velocity couldn't really be used very practically is this case here of a person running on a running machine. If we're to hang that running machine up on bungee cords, the whole thing would be bouncing around. That would make it very difficult for the person to run on the running machine, and it would change the nature of the source input internally. And this doesn't just happen for running machines, this can also happen with machines which have pistons inside them moving up and down, where the actual inertial force of the engine moving up and down can affect the source operation quite significantly. So in some cases, I'm not ruling out free velocity altogether, but it's common for us to encounter a situation where we need to run something under load, or where the internal vibration mechanisms could be affected. where the free velocity is a problem to measure. An alternative to the free velocity is the block force. We would measure that typically by putting a force transducer under the contact points of the machine to the floor. And in this case, we need to block entirely the motion of the floor by having a very, very heavyweight structure. So in a test experiment would look quite similar to this. Basically, we need the mobility of the support, in this case, to be much, much, much lower than the mobility of the source itself, in order for us to be able to measure the force with that load cell with no movement in the supporting surface whatsoever. There are certain circumstances where these measurements are made, but depending on the type of source, again, this can be somewhat impractical because you need such heavyweight structures to actually truly block the vibration of the source. There are some examples in automotive where they build a massive concrete block and attach a vehicle suspension to it and run it on a rolling road. But again, this sort of measurement, they're quite expensive, quite complicated to set up, and there are other ways of doing it, which we're going to look at. So first of all, we're going to look at the reception plate method, which is the approach which has been developed at Liverpool University. And the reception plate method is an engineering method intended for the characterization of structure-borne sound sources. The method is simple to implement with moderate expertise and standard measurement equipment, and it's widely used for characterization of structure-borne sound sources used in buildings due to its simplicity. I think it was mentioned in Josh's presentation that basically structure-borne power transmission from a structure-borne sound source into a receiver structure depends on the receiver structure as well as the source. So it's not straightforward as airborne sound transmission where the receiver is always air. But because people got so used to methods of measuring airborne sound power, they want something equally simple to be able to characterize a structure-borne sound source. So that's what it says in the second bullet point. It's basically, in general, engineers seek methods for the prediction of structure-borne sound, which are as straightforward as for airborne sound. And this has basically been the main driver for the development of the reception plate method, to provide simple methods that work well. Okay, so the reception plate method is written up into the British and European standard 15657. So if you want to read up on it, you can look at the standard and follow the procedure. So I'm just going to give a broad overview of what the method is and how it works. So the reception plate method essentially allows a determination of single equivalent values to describe source activity and passive properties of the source. They include block forces, free velocities and mobility, all as single equivalent values, and it allows us to do these measurements under realistic mounting conditions, and it totally avoids any requirement to measure any forces directly, as would be the case for other methods. Everything is a response-only measurement, which makes things much simpler. So the basic theory behind the reception plate method is that the power transmitted from a vibration source into a reception plate structure is equal to the damping loss factor of the plate multiplied by the angular frequency omega, m the mass of the plate, times the spatial average velocity squared of the reception plate. So we can work out the power transmitted from a source into a reception plate, but this power will not be the same for a different reception plate. But at least it's something we can calculate according to this equation. I'll just mention that the damping loss factor there can be easily calculated as well without applying any forces. It's essentially an equation which, to solve it, we just need the reverberation time of the plate, and that can be obtained in exactly the same way as you would obtain the reverberation time of a room, but using accelerometers on the plate instead. So reception plate can take on many forms. There's two examples here. The one on the left is a very lightweight reception plate with perforated holes, so there's no acoustic loading. And the one on the right is a 20mm thick, much heavier reception plate. And the two sources in that case, the one on the left is the pump we saw earlier, and the one on the right is the large fan. And if we look at this plot here, this is the mobilities of the high and low mobility reception plate. You can see the dark black dashed line here is the low mobility reception plate, so it has a much lower mobility than either of the sources. And the high mobility reception plate has a much higher mobility than either of the sources. And that allows us to create two measurement conditions, one where the source has a higher mobility than the receiver and vice versa. So what we know from the block force, from the reception plate method, is that the power transmitted to the reception plate is equal to the loss factor omega, the mass of the reception plate, multiplied by the spatially average velocity squared on the reception plate. So if we take the case of a reception plate which has a much lower mobility than the source, i.e. the source mobility is much higher than the receiver reception plate, the equation for power into the reception plate simplifies to this form, where the block force, the power transmitted, is equal to the block force squared times the mobility of the reception plate. So if we know the mobility of the reception plate and we know the power transmitted, which we can obtain from the measured velocity squared on the reception plate, we can rearrange this equation and we can find the block force of the source. An example of that being done is shown here. This is for the fan on a low mobility reception plate. And the black line in the right figure here is the directly measured exact block force, and the dashed line is the estimated block force single equivalent value obtained from the reception plate method. So that shows that we can make a good estimate of the block force of that particular source using the reception plate approach. Another thing we might prefer to do, depending on whether we use a heavyweight reception plate or a lightweight one, is we could also measure the free velocity of the source. So in cases where the mobility of the receiver is instead much higher than the source, it's a simple matter of attaching a couple of accelerometers, well, one accelerometer at each of the contact points between the source and receiver, and measuring the spatially averaged velocity squared of the velocity at the contacts between the source and the receiver. If we have a situation where we don't have a reception plate where the mobility is much higher, we can instead just put some rubber isolators there, or even you could suspend this source on bungees just to ensure this is entirely free. And as mentioned previously, you can make some excitations on the source and you can look at the natural frequency of it. And providing the source is free in the frequency ranges you're interested in, you should get a good measure of the free velocity squared from the reception plate. Here's an example of that, which is the fan on the high mobility reception plate. And the black line in this case is the free velocity measured with the fan hung on bungee cords, so the normal direct measurement, which may or not be possible in all cases. And the dashed line is the estimate of the free velocity from the reception plate method, well, which is directly measured at the contact feet whilst on the reception plate, the high mobility reception plate. Then a useful equation is that if we know the free velocity and we know the block force single equivalent values, it is actually possible to determine the single equivalent mobility of the source itself using this equation. So having measured the free velocity and the block force, we're able to also calculate the single equivalent mobility of the source. This figure shows one example of that. The grey lines is the multiple measurements of individual mobilities of each corner of the fan. The black line is the single equivalent average of those points, and the dashed black line is an estimate of the single equivalent mobility from the reception plate. This figure is similar. It's exactly the same line colours, but in case this is for the small pump, and you can see that very good agreement between the solid black line and the dashed black line, which is the data we need for predicting structure-borne power using the reception plate method. So using the reception plate method, we basically need to measure 2 out of the 3 quantities, and then we can always calculate the third one. So we essentially can choose which of these 2 are easiest to measure directly, and then it will allow us to calculate the third. So then by measuring any 2 of those quantities, you can fully characterize the source in terms of both its passive and active properties by convenient single equivalent values. So the advantage of the reception plate method is that the calculations are very simple. The equipment requirements are really low. You only really need 1 channel and 1 accelerometer. You don't even need to have an FFT analysis software package for making the measurements. You can make all measurements in 3rd octave bands. This makes it really straightforward to implement using basic equipment. Another useful thing is that the data which comes out are convenient single figure values with no phase information, which is really easy to understand in 3rd octave bands and should be familiar to most people. And generally what we tend to find is that there's such a broad variation in installations in building acoustics, and there's actually much more uncertainty that comes from the variability of the receiver structure, that the accuracy of the characterization using reception plate is higher than the variability in the receiver, so it's perfectly adequate for making predictions of structure-borne noise in buildings. There are some limitations, however, though. It's not always practical for sources with unusual couplings, for example, automotive components, and we're going to see an example of that when I go on to the other method. For example, an engine in a car will have engine mount points at its base, but also probably halfway up the engine at the back, and it can't just be rested on a plate. The use of single equivalent values and neglecting phase does lead to higher uncertainty than when you do include it. And the reason they choose to do that is for the amount of simplicity it gives. But if you really want really accurate results, you do need to include phase as well. A requirement for the method for getting good single equivalent values for mobility and free velocity is that we don't really want the free velocity or mobility of the contact points to vary too much between one point and another. And that means those average values are representative of all the contact points. So machines with very, very different contact feet and perhaps not quite so well suited to the approach. And the only other downside is that it basically doesn't provide the accuracy of prediction or the flexibility required for some industries where the variability of the receiver is much lower. So cars coming off a production line, for example, will be much more similar than different buildings. So automotive applications and rail and aerospace do potentially warrant a slightly more complicated method. So now I'll talk about the in situ block force method, which is what we refer to as a precision method for the characterization of structure-borne sound sources. The method is more challenging to implement than the reception plate method and requires significant user experience and more sophisticated equipment. It's widely used for the characterization of structure-borne sound sources in automotive and rail applications, and this is due to the higher accuracy of the method and the lower uncertainty in the receiver structure. The in situ block force method, ISO 20270-2019, was standardized last year. It comes from work which I did during my PhD. I started PhD in 2009 and completed in 2005, started, completed in 2009. And for the last 10 years, I've spent improving the method and getting better and better results. The basic premise of the method is that if we have a vibration source, which we're calling S here, and a receiver structure R, these can be this could be an engine, for example. This could be a plate or a car or a test bench or a train, whatever. When the source and receiver are combined together, we refer to that combined system as C, which is the coupled assembly. The source and receiver couple through this interface through multiple degrees of freedom C. Using reception plate method, that interface C would be described as a single equivalent value. When using the block force method, we don't consider it the coupling between the two as a single equivalent value. We look at it as multiple contacts in multiple degrees of freedom. The theory that was developed to obtain the block force in situ can be found in a, I think, 2009 paper by Andy Morehouse and myself. There's also some stuff in the thesis, and then much more that comes afterwards. But what we basically proved was that the block force can actually be measured in situ. So if we measure the mobility on the assembly at the coupling point between the source and receiver, we can and then invert that matrix and multiply it by the velocity at the coupling points. We're able to work out the block force. Now, the color code in here is red if it is a property of the source, green if it is a property of the assembly, and blue if it is a property of the receiver. So what this shows us is that we can obtain a property which is solely of the vibration source from measurements on the coupled properties of the combined source and receiver. Once we've obtained those block forces, it's possible, if we make further measurements on the assembly, for example, exciting at the interface C on the coupled assembly and measure the sound pressure at D, we can measure a vibroacoustic frequency response function. And if we multiply this is a property of the assembly again, and this is the sound pressure measured at D. If we multiply the block forces by H-C, which is the relation between C and D, we get the sound pressure at D. In practice, though, if you were to do all those measurements, you obtain the block force of the source, and you were to measure multiply that by HC to get PC, why didn't you just measure the sound pressure at D when the source was running, and you'd have obtained that anyway? So what we actually want to be able to do is combine measurements made on the independent source and receiver structures. You can see red and blue, in order to predict this thing HC that allows us to make a prediction of sound pressure for the source in different assemblies, providing we have knowledge of the receiver mobility and the receiver frequency response function. So in this example, we have a train, which we refer to as the assembly C. In this case, the receiver is the car body, the train, and the source is this air compressor, which runs the brakes and things like that, which is attached to the underbody of the carriage. We want to know what happens when the source A is coupled to the receiver B, making the assembly C, the assembly of the train, but without having to actually physically connect A and B. So from making measurements on A alone and B alone. So in order to do this, I flew out to Turin with a view to obtaining the source block force from measurements on one of Wabtec's test benches using this equation. The other thing I needed to obtain while I was there was the source mobility, because I'm going to need that as well in the calculations, but I'm just concentrating on the measurements of the block force here. First of all, you can see from this piece of equipment, its mounting points are here and here. There's a lot of it that hangs down afterwards because it hangs off the bottom of the train. So you can see that in this case, it would be relatively impractical to mount this to a reception plate unless you had a reception plate with a big hole cut in the middle, which would mean developing a bespoke reception plate for this specific source. Also, I mentioned that it's important in our case for more complex machines that have been attached to better defined receiver structures that we want to know how much force is being transmitted by each contact point individually, and not just each contact point in a specific direction. So you can see here are the 4 contact points between the source, which is the grey part, and the white part, which is a test bench. And you can see that there's multiple accelerometers attached. Here there are 1, 2, 3, 4 pointing in the vertical Z direction. There's 1 pointing in the X direction, and there are further 2 pointing, not so clear on that figure, further 2 pointing in the Y direction. If you look at the close-up at the bottom, 5 and 6 accelerometers are pointing in Y, 1, 2, 3, and 4 are pointing in Z, and number 7 is pointing in the X direction, but it's just oriented slightly different. So using a modal hammer or instrumented hammer, we go around those points one by one, exciting them in the X, Y, and Z directions. And if we look at the difference between, for example, accelerometer 2 and 4, subtract one from the other, we can work out how much of a rotation about that bolt there is as well. So not only do we capture vibration in the X, Y, and Z directions, we also calculate vibration rotations about the X, Y, and Z axes as well, giving us 6 degrees of freedom per connection point. Whilst I was in Italy, we needed to measure 2 things, one being the block force and the other being the source mobility. So the first measurement we did was to mount the air compressor on air springs, as can be seen here. Air springs give us a really nice, very low natural frequency for a very heavyweight piece of equipment. So you can see here that we wouldn't have been able to hang this machine on bungee cords. So whilst in this test setup, we measured the mobility of the source YS as a 28 by 28 matrix. But we also, whilst it was resiliently mounted, measured the, so in this case, YC is basically equivalent to the source mobility because it's freely isolated. And then we measured VC, which is effectively the free velocity in this case, and we use that to calculate the block force in this free condition. That's shown in the blue line in this plot here. We then rigidly mounted the machine onto the test bench, so it's no longer free anymore, and we repeated the measurements to obtain YC, which will include properties of the source and the test bench combined, and then measured the operational velocity at each of the points, inverted the matrix to calculate the block force. And you can see that from the 2 very, very extreme conditions, totally free and quite rigidly blocked, but not perfectly blocked, we get the same block force in situ from the 2 measurements. And that shows us that the block force we are measuring is in fact an intrinsic property of the source, not dependent on the mount condition under which it is measured, which is what the theory was developed to do. So the next job is we want to predict the structure-borne noise on the train. This is not the actual train, obviously. I can't show a picture of that. What we have measured already is YS. So we got YS and that YS from measurements in Italy. So we're going to Poland now, to Katowice, where the train lives, to measure the vibroacoustic frequency response function of the train without the compressor and the mobility of the train without the compressor. We can combine those then to determine what is the relationship for the coupled structure where force is applied to the junction between the 2 and the sound pressure is measured inside the train. So that's what this figure shows. We've got a 28 by 28 matrix for the source measured in Italy, a 28 by 28 matrix of measured mobilities for the train. That's a photo of the measurements on one of the contact points on the train using the same accelerometer positions. And then we've got HR, which is a 28 by however many microphones or responses you want matrix, measured between the interface degrees of freedom and the responses that we're interested in. In this example, we're looking at the spatial average sound pressure level within the train, the black line being HC, which is directly measured on the train, and the red line being the prediction of HC, obtained by combining the measurements done in both Italy and Poland. You can see that we get a good prediction of the sound pressure inside the train to a unit force for this specific direction. So now we've measured this vibroacoustic frequency response function. We determined it from measurements on the source and receiver, and we've got the block force from the measurements in Italy, which have been validated. We can now multiply this vibroacoustic frequency response function by the block forces that we obtained, and we can use that to make a prediction of structure-borne noise inside the train. So this is inside the train. It's not finished fitted out yet. This was done as a validation measurement for testing the method. There are 3 microphones hung inside. And on the next plot, you're going to see the actual measured sound pressure level on those microphones. The average sound pressure level is a black line on the figure, and then that will be combined to a red line on the figure, which is the prediction of the structure-borne noise inside the train. So the top plot is a narrowband representation of that. The black line is the sound pressure level measured in the train. The y-axis is hidden because it's confidential, and the red dashed line is the prediction inside the train. The top plot is narrowband. Probably easier to look at is when the narrowband data is converted to 1/3 octave bands. And our aim in this experiment was to get a good agreement between 100 and 1000 hertz, because we knew that was the frequency range of interest for this specific structure-borne noise source on a train. So we didn't optimize our results for this frequency range for the sound pressure level, and it would have been difficult to do so because we were making measurements in a very noisy factory. But in terms of the A-weighted overall sound pressure level within the train, red line and black line measured and predicted. If you sum up all those 3rd octave bands of the A-weighted sound pressure, in that range we were interested in, the prediction of the structure-borne noise inside the train was within 3 dB of the measured. It's actually 2.6 decibels. And that's despite the compressor being, the compressor that was measured on the train in Poland wasn't exactly the same as it wasn't the same unit as the one tested in Italy, and there were very small differences between them. Similarly, for floor vibration, we measured the floor response, because they're also interested in tactile vibrations within the train, and we're interested in those below 100 hertz because that's what a human will sense. So in this result, it's similar to sound pressure, but we're looking at the black line is the average of the X, Y, and Z vibrations combined, directly measured on the train floor. And the red dashed line is a prediction of the vibration of the train floor. Just the same, top block, narrow band as before, and the bottom plot, 1/3 octave bands. And now the frequency range we're interested in for tactile vibrations, which humans can feel, is in the range 0 to 100 hertz. But in this case, we're only really interested in 10 to 100 hertz, because the compressor operates at such a speed that it's not really exciting any vibrations below 20 hertz at all, really. So that gives you an idea of the sort of more complex application of this more complex method to obtain really accurate predictions of structure-borne noise and structure-borne vibration within inside a train using independently measured properties of source and receiver. So just onto the advantages and disadvantages of the block force approach. First of all, it handles complex geometries and multiple degrees of freedom really well, because we're not confined to things that can only sit on a plate. It takes into account magnitude and phase. That means if there are two feet of the equipment which are vibrating oppositely at the same frequency, they could potentially cancel via a transfer path to the interior, and it takes into account that cancellation between contact feet and the interior. So the phase for some applications can be very important, and by taking this phase into account, we can make high accuracy predictions of interior noise and vibration. Another useful thing it allows us to do is if we do make a prediction of structure-borne noise which is higher than we would like, we can actually look at which of the individual feet or degrees of freedom is responsible for the power transfer which causes the higher level of noise inside the train. So it's also a useful diagnostic method. So as mentioned before, the approach is usually used mostly for applications where there is low variability in the receiver structure, so it is worth the effort to get a much more precise estimate of the block force, which takes into account both magnitude and phase. The drawbacks are that it's challenging to implement. You can see for that particular experiment, we used about 40 channels, FFT analyzer from Brüel & Kjær, multiple accelerometers, probably a good £100,000 worth of equipment to make the measurements, and a lot of work in data processing. When it comes to inverting the matrices, if you do not have really good data quality, or if you make one mistake on sign convention in the matrix, everything goes completely wrong, so you need to be extremely careful. It requires quite a lot of experience, experience using the hammer to get good frequency response function data. If you put bad data in, you do not get good results out. And it takes probably a few years to get experience to use the method. Again, I've mentioned already that we also need to have a high investment in equipment, which includes multi-channel FFT analysis, multiple accelerometers, force hammer, instrumented hammer or shaker, and probably some software modules that you wouldn't normally have on a sound level meter. So good results, but challenging and expensive to implement. Sorry, my final slide. So a summary on what I've been through in the presentation is basically what we've been saying all week is structure-borne sound sources need to be described in terms of active and passive properties. Martin has spoken about how you might measure or model those passive properties, and in this presentation we've looked at how we might obtain these active properties. The active properties generally cannot be modeled. It's, for the time being anyway, it's always going to be easier to measure these active properties rather than model them, because the machines are too complicated on the inside to model easily. So then if we can't model them, how are we going to obtain them? The free velocity method has its limitations, especially when machines want to run under load, and the block force method has its limitations because it's challenging to actually block a source and directly measure the force by a force transducer. Most people don't have a bag full of force transducers already. So the reception plate method is a really practical solution, yielding all the required source characterization, source mobility, free velocity, block force. Application is straightforward, requiring only basic equipment, third octave band analysis, and one accelerometer. The uncertainties are not greater often than the variability in many receiver types. So the accuracy of prediction of structure-borne noise is generally adequate for a lot of building acoustic applications. The second one I talk about is the in situ block force method. It also provides all the required active and passive characterization data, and the method is very accurate, but it's sensitive to the data quality and it requires really sophisticated equipment. On the upside, the uncertainties are low, so it's very well suited to precision engineering and high-tech applications where variability in the receiver is low. And that's the end of my presentation. I'm happy to take any questions. I can just share an example of a video, if I can get Zoom back up. And I'll share this one with computer sound. So I think it's probably fairly clear, but it's quite nice to see this result of a measurement of free velocity. So you can see now that the pump is hung up on bungee cords as before. There's an accelerometer on 1 foot. There is a little bit to run against load against anything else. And to get the sort of spatially averaged free velocity from this source, you would measure once with the point, and then you can average those to get a mean overall. So I'll take any questions.
There's one question from Bill there about how did you eliminate an airborne component when you were measuring in the train carriage?
That was a bit of a challenge. So there is an airborne component which is present in the black line, but not in the red line. So the prediction, which was the red line, should only include the structure-borne component. So we wouldn't necessarily expect a perfect agreement between measured and predicted, because the measured includes the airborne flanking as well as the structure-borne transmission. But because it's a sealed unit, for that frequency range above 100 hertz, the structure-borne noise is known to dominate in that train. And we did make efforts to block up all flanking paths as best we could, but obviously you can't stop that getting through at very low frequencies. Yeah, I can talk about the video again. So the video was just showing that the measurement of free velocity on sort of bungee cords. You could see as the pump was running, as it first sort of fired up, it started to it just sort of kicked to one side, but then it sort of went into sort of stable operation. And for that case, you could get a fairly good measure of the free velocity. And basically, when you're doing those measurements, if you're doing it, if you just want a single equivalent value, you can just put one accelerometer on 1 foot, run the machine, get the 3rd octave band spectrum, which is shown in Martin's figure here. So that's the free velocity measured in narrow band. 4 different connection points, each measured 1 by 1 in turn. You convert that into 1/3 octave bands, each of those spectra, sum the squares of the vibration velocity on the feet, take an average, and then this is the velocity squared plotted in decibels in 1/3 octave bands.
Okay, any more questions are welcome, but thanks, Andy, for taking us through from a practical approach to that highly complicated precision approach in the end. Perhaps we should mention that the reception plate idea was meant to be an isolated reception plate, so that your reception plate would be on some kind of resilient material, preferably viscoelastic material that give damping as well to your plate. But in principle, you could use it if you had a nice clean concrete wall and you wanted to fix your boiler to it, and even if it was connected to all other walls and floors, if you were very careful and used a calibrated source, you could still use a wall in a building that was coupled to other ones. The reason we go for isolated plates is that when you put a machine or something on that plate, if it's coupled to other walls and floors, then all the energy, vibrational energy, goes off there, and eventually it does come back to the plate. So it makes it difficult to get accurate structural reverberation time measurements, and also at low frequencies you end up with biased vibration measurements as well. But that, there is potential to make it even more simple with the reception plate if you've got a calibrated source.
Yeah, I think one thing probably I should mention as well is that experiment on the train there used 7 accelerometers per foot, so 28 accelerometers to determine translations in X, Y, and Z and rotations at each coupling point. As part of the project, we also looked at eliminating some data from that data set to see what were the consequences of not including rotations or not including in plane motions, things like that. And for each time we stripped a little bit of data out of the matrix to make the calculations, the result got a little bit worse. So it did sort of show us that, unless you're really going to put the effort into doing, for this specific case anyway, unless you're going to really put the effort into doing it properly, something like the reception plate actually could give just as good results as a poor implementation of the block force method.
Right. Oh, interesting. Okay, good. Another question. Can you read it, Andy?
So given the high degree of sensitivity of the block force method and perhaps a somewhat high risk of calculation error, would you always validate with SPL measurements? What I would normally do is when I'm measuring the block forces, and I didn't have a slide in this presentation because I thought it was getting long enough, I would measure the block forces at the contact points at the machine, but also whilst it was on the test bench, I would have a few reference sensors on the test bench, and I would look at the frequency response function, transfer functions between those coupling degrees of freedom and the response point on the test bench to ensure that I can validate my measurements on the test bench before sharing the data. So in this case, I've shown we've checked that the interior noise prediction on the train was good by measuring the sound pressure level. But what I would normally do is check that the block forces predict the vibration level on the test bench accurately. And from that, I would then say that I trust the block force data. The other validation cross-reference I've got, of course, in this case is the free velocity, the block force calculated from the free velocity being the same as the block force calculated from the rigidly installed condition. So it says, are there any methods that could alleviate or bring more confidence during testing, since one looks like it wouldn't know if it's going well and correct until the measurement campaign is complete? Well, the method is basically that onboard validation, and which is the approach of measuring the vibration response on the test bench. Specifically for that, it's described in the ISO standard actually. Yeah, and also Josh has said there, I don't know if you want to use words, Josh, but you've spent a lot of time, haven't you, trying to develop methods to make sure that we're including the correct degrees of freedom at the interface. And go on, Josh, I'll let you explain because it's yours.
Yeah, so there are a few kind of simple data checks that you can apply to your measured mobility matrix. just to check that you've done everything right and the data is good. One of those is to check that the matrix is reciprocal, which just means if you interchange the excitation and the response position, the transfer function should be the same. So you can just compare, maybe the element in one corner of the matrix to the other corner, and they should be the same or very similar. And if they're very different, that would kind of indicate an error in your measurement. And there are other things you can do quite similar to what Andy just said, which we call the onboard validation, where we can check that we have enough degrees of freedom at the interface. That's kind of one of the main sources of error. If you don't include all of the important degrees of freedom, you can end up with kind of bias errors on your blocked force, which then kind of propagate all the way through and can give you kind of errors in any response predictions. So there are methods for kind of checking the completeness of the interface as well.
Probably, Josh, it's probably worth you also mentioning, given that we haven't got another question at the moment, that the receiver structure doesn't have to be a measured structure. It could come from a finite element model, or it could come from a statistical energy analysis model, or from a hybrid model, which are things that which are often used in the sort of automotive and aerospace and rail industries. So that frequency response function that I calculated in this case from measured data, HC, is quite often also modelled in those industries. In which case you only need the block force of the source and the source mobility and the model.
Okay, so today, we've split it into those kind of passive properties and those active properties. And the next stage on Friday, we're going to move towards propagating that structure-borne sound power through a structure. And how can you predict that? And then we're going to look at sort of more practical noise control and isolator performance again. But probably at this point, we're probably leaving the source characterization. So if there's anything about the passive properties that we reinforced first, and then those active properties, if you want to pick up anything else on that, please go ahead with a question in the chat. Andy, there's another one for you there.
What's this one? Sorry, Andy, are those model receivers not then subject to uncertainty for the high precision industries, or do they have very precise models? I think I'll probably let Josh answer that. The whole point of those models are subject to really high uncertainty, and it's a really important thing to take that properly into account. So what you would do is model multiple systems. SEA effectively gives you the mean anyway, but you would also have to, if you were using FEA, you would probably have to model multiple FEA systems, varying material properties.
I mean,
well.
Andy, just to answer that, I mean, that's we talked about it in the source presentation, where we had the FRF, the FE generated FRF of a pane of glass. That's even for a simple system. If you do an FE model, you model one set of parameters at a time. So you might have to do your sort of randomized, your Monte Carlo type arrangement to get that distribution in FRF. So it would still be subject to uncertainties, but you'd have to think about how you capture it. Do you capture it by running a number of simulations with randomized inputs, or do you take mean responses and things like that? So there's still things to consider from my point of view with those receivers.
There is what you would do. One thing you can do, and I'm sure Josh will have more to say on this, is that you could run multiple models, do multiple predictions of the block force, and then you could look at the most likely scenario of how bad it might be.
Yeah, so one thing you can do, like Martin just said, if you had, say, a finite element model for your receiver structure, and you had some idea of what the tolerances might be, in that structure, whether it's density or geometry or other material properties, you could run a Monte Carlo simulation on your finite element model for the receiver. You could use that to get the mobilities, so the receiver mobility, and you could also get some measure of the uncertainty. Perhaps it's just a standard deviation or a variance for each of those mobilities that you need. And then there are methods for combining the uncertainty of the receiver with the uncertainties in the mobility. And you can actually propagate all of the uncertainties through and get a response prediction, perhaps with a confidence bound, which would take into account the uncertainty in your receiver, but also your blocked forces. So there are ways of propagating experimental uncertainty through this whole kind of procedure.
That's basically been a lot of your work for the past 2 or 3 years, is working out how to do a lot of that stuff, Josh.
Yeah.
So if you want to read up about that, you'll find multiple papers by Meggitt on propagation of uncertainties using combined, measured and model data. But you very good question. There's uncertainty in the models, yes, unfortunately. But you can look at worst case scenarios.
Okay, any more questions?
This isn't a question.
Sorry, I was going to. There's another way of handling uncertainty. If you look at the reception plate method, at this moment, there's a round robin exercise going on with European laboratories where they send the same source to each laboratory and ask it to measure its blocked force and its free velocity, and it's called reproducibility, and that gives you an indication of the uncertainty associated with that method. In fact, most standards require some estimate of uncertainty of the method that's been proposed.
Josh, did you have something else to say?
Yeah, I just wanted to add one quick thing regarding the advantage of using this more precision method. And that's because you're retaining all of the phase in all of your quantities. You can actually build what we would call a kind of virtual acoustic prototype of the system. So you can actually listen to the structure perhaps before it's even been built by retaining the phase. And that's quite useful because if it's, say, an automotive case or a domestic product, you can try to get an impression of the sound quality without having to physically build the structure. But to do that, you need to include the phase in all of your kind of components. So that's perhaps just another advantage of the precision method, albeit it takes a lot of effort to do that.
Yeah, I should have mentioned that probably. You're right, Josh. One of the things when it comes to sort of automotive applications and things like that, they're often not so worried about how loud or quiet something is. Obviously, that's a consideration, but the sound quality is really regarded just as critical as the loudness is only a part of the sound quality. So the possibility to be able to oralize and listen back to how that piece of equipment will sound when it's installed is another really useful thing that comes from retaining phase information in the calculations. But again, it comes at a cost of the considerable increased amount of effort